In these 6 short minutes, I want to tell you a little bit about my research. And more specifically, I want to talk to you about pupillometry, so measurement of the size of the eye's pupil, and how you can use pupillometry to decode where in space people are attending to, and in turn, how you can use that to implement a human-computer interface. So what I will talk about is the pupillary light response, or the pupillary light reflex. And I think you all know what it is. If it's dark out, right, if it's night, then your pupil dilates, your pupil becomes big, because there's not a lot of light available, compared to when it is bright out, right? When you're out in daylight and your pupil constricts, or it becomes very small. And this dilation of the pupil in response to darkness and constriction of the pupil in response to brightness is called the pupillary light response, or the pupillary light reflex. Now, you probably know that this happens, right? That your pupil responds in this way if you look directly at something that is bright or dark. But what you may not know is that this also happens if you covertly, without making any eye movements, covertly attend to something that is bright or dark. So, for example, in this, if we look at this example, imagine that we have someone who keeps her eyes on the central fixation dot, and on the left side we have this dark picture, and on the right side we have this bright picture. And then she is covertly, so without making any eye movements, from the corner of her eye, attending to this dark image. Then the pupil is a little bit larger than when she would be covertly, so from the corner of her eye, attending to this bright image. Right? So that's an effect of covert visual attention on the pupillary light response. To tell you a little bit about how we can study this in the lab, basically we can do exactly this experiment in the lab. So what we do is we show participants a display that is divided into a bright and a dark half, and then we ask the participants to keep their eyes fixated on the central dot, right? So they're not allowed to make any eye movements. And then we tell the participant, please either shift your attention to the dark side of the screen, so indicated by this blue arrow, or to the bright side of the screen, right? So while keeping their eyes in the center, just a mental shift of attention. And then what we do is we measure pupil size, and then we can plot pupil size here on the y-axis as a function of time here on the x-axis. So time 0 means that's the moment that we ask the participant to shift their attention to the brightness or the darkness. And then what we find is that the pupil is a little bit larger if the participants attend to the dark side of the screen, this blue line, compared to when they attend to the bright side of the screen, this orange line. So that's the effect of covert visual attention on the pupil light response. So that's pretty cool in itself, right? It's a very fundamental property of how the human visual system works, I think. But we can also use this to implement a human-computer interface. So a way for participants to interact with a computer just by making these very small fluctuations in pupil size and no other movement. Now, and the way we do that is essentially, again, using a very similar experiment. So we have a participant, and the participant has to keep the eyes in the center on the central fixation dot, and then we have what you could say is a virtual keyboard. So we have a bunch of letters on the screen. Here I have 2 letters, but you can do it also with more letters, but I will show it with 2 letters just for simplicity. And then we ask the participant to write a letter by covertly attending to it, right? So mentally selecting the letter without making any eye movement, without moving any part of the body, just mentally selecting the letter that the participant wants to write. So say that the participant wants to write the letter A, then we can measure the size of the eye's pupil, right? So that's what we have here. And the pupil has a certain size, but that's by itself not terribly informative. But you can see that the A right now is on a bright background. And what we can do is we can flip the background around. So now the A is on a dark background. And what we then expect is, because the pupil was previously attending to something bright and now to something dark, that the pupil should dilate a little bit. So we predict, here you see predicted pupil size, basically. Then if we flip it around again, the A is on a bright background, so we expect the pupil to constrict a little bit again, right? And we flip it around again, now we expect the pupil to dilate again a little bit. In other words, we expect the pupil to oscillate along with the brightness of the letter that the participant wants to write, the letter that the participant mentally selects. Now, of course, if the participant had been wanting to write the letter B, the pupil would also have oscillated, of course, but in counterphase, because the B oscillates in counterphase. So what we do is very simply, we measure what the pupil actually does, and we determine whether it looks more like the green line, A, in which case we write the letter A, or whether it looks more like the red line B, and then we write the letter B. Now, this works with 2 letters. It's a very simple principle. But we can also do it with more letters. So say that we have 4 letters. What we then do is essentially we divide the 4 letters up into 2 groups. In this case, the H and the D, and the B and the F. And then we eliminate one group. Right? So we eliminate half of all options. We end up with 2 options. We eliminate again half. And we end up with the target letter. So if we want to make a selection out of more than 2 letters, what we do is all the time divide all the options into 2 groups, eliminate one group, divide what is left up in 2 groups, eliminate half, etc. Until we end up with the letter that the participant wants to write. Now, so how well does this work in practice? So what we did is we conducted a training experiment, quite a long training program. And this was a pre-registered training program. Pre-registration means that before you actually start collecting data, you specify exactly what you're going to do and what your criteria for success are, etc. Right? So that you cannot, after the fact, make your algorithm look better than it actually is. And then what we found, basically, we had 10 participants that we asked to participate in this quite long training program. And we found that 9 out of our 10 participants were able to write complete sentences using a virtual keyboard of the type that I just explained to you, but then with many more options. So all 26 letters plus a bunch of control characters like backspace, space, enter, etc. Right? So you can really use this. It really works in practice with naive participants after a bit of training. Now with that, I would like to thank you for your attention. If you want, there's a video of this system in action on my website and lots more of information. So thank you very much.